Our next speaker is Boyou Hou. He's a PhD candidate at CFM, and his research focus is on thermoelectric fire retardant materials for smart fire prevention and early warning systems. Boyou, I'll let you can start sharing your screen.
Okay.
Yep.
Thank you, Sajni.
Yep.
I'm sharing. I'll say the.
Yes. Yeah, we can see your screen. Yeah. All good.
Okay. Thank you, everyone. Thank you, Sajni. Thank you, Molly. Good afternoon, and thank you, everyone, for being here. I'm Boyou. Today, I will share our work on mechanism-guided thermoelectric strategies for smart fire prevention. Sorry. Many of us have smelled smoke before we saw flames. When that happens, we are already late. In recent years, such as during Australia's Black Summer and the large losses reported in Los Angeles, we learned that fires can move faster than our warnings. In cities and at the wildland-urban interface, wood-framed buildings can ignite and spread fire very quickly. Evacuation becomes hard, and firefighting becomes dangerous. So we ask a simple question: can we get a reliable warning earlier, even in tough outdoor places, and do it without depending on the power grid? Our answer is to use thermoelectric sensing. A thermoelectric material turns a small temperature difference directly into a voltage. We use that voltage to raise an early warning before smoke is visible. Thermoelectrics convert a temperature difference directly into a voltage. This gives us features that matter for safety. First, they can power themselves. When there is a heat gradient, there is energy. So we do not need mains power or a battery. Second, they respond quickly. The signal appears as soon as a temperature difference starts, which is before thick smoke fills a detector. Third, they fit many formats. We can make coatings, thin films, and textiles and place them where heat builds up first, such as eaves, vents, and the building's surface. Finally, the output is a direct voltage. A very small circuit can use it to trigger an alert or send a message to the cloud. Next, I will briefly show a few mechanisms for designing thermoelectric materials and devices. From this slide, I'm showing some research work that using structural design methods. The idea behind these studies is simple: make continuous layered or porous networks. This raises electrical conductivity, gives a strong heat to voltage signal, layer for protection. We can see from pattern A, researchers begin with a graphene oxide film and use a mild chemical treatment that partly reduces the shades and tightens their contact, which raises electrical conductivity and strengthens shade-to-shade stacking, like hydrogen bonding and pipette stacking. And from the pattern B, a conductive polymer, PE dot, coats reduced graphene sheets in a layer film held by a cellulosic binder. The polymer supplies continuous charge lanes. The graphene sheets act as high mobility bridges, and the layered interface couple quickly, so the voltage builds within seconds. Together, these steps create a denser, more conductive network that gives a clear voltage temperature differences, and the coating forms a protective char at high heat, which supports faster and safer lamps. From the pattern C, uh, a light aerogel provides high surface area and many conductive contact, so small thermal changes are captured quickly. When heated strongly, the calcine converts into a dense char that protects the substrate and locks the framework in place. And the second mechanism is energy filtering. Energy filtering is like using a sieve. We add gentle barriers so that high energy charge carriers contribute more than low energy ones. When we do this while the feedback coefficient goes up, so we get more voltage per degree of temperature difference while keeping enough conductivity, so current can still flow. Researchers built a sandwich-like structure, mixing sheets on both sides, and a web of multi-watt carbon nanotubes in the middle. The key is the height and the spacing of those barriers. If the barriers are too high or too dense, the current becomes too small. If they are too low or too sparse, the effect is weak. We tune this balance so that even a small early temperature difference creates a clear voltage signal. That signal is strong enough for a simple circuit to warn the fair. And the third mechanism is doping modification. Doping is not just about adding as many carriers as possible. We set the carrier type and the amount so that conductivity stays high, but the feedback effect coefficient does not collapse. One of the attempts of this mechanism is inorganic ion doping. This line of work adds metal ions, for example, calcium with chloride, to the polymer network. The ions coordinate with the chains and act like tiny crosslinks, which creates extra charge carriers and raises electrical conductivity while keeping the film more stable at high temperature. The other attempt of this method is organic small molecule doping. Here, small acid molecules stop the conducting polymer, tuning carrier density while preserving chain stacking. Both the routes use doping to set carriers and stability at the same time. Metal ions give coordinated networks. Small molecules give quick response and strong voltage, which provided we avoid overdoping and ensure good compatibility. This slide explains the ionic thermoelectric effect. When one side is warmer, cations and anions move different in the liquid or gel. If they move at different speeds or directions, charge separates and a thermal voltage appears. A common trick in the literature is to hold one ion more tightly than the other. For example, charged groups on the polymer can bind calcium and confine chloride near the chains. The bound ions move less. and the other ions moves more, and the Seebeck coefficient increases. Because the effect is driven by entropy, it can give a large voltage even at small temperature differences. With good encapsulation, the response is repeatable outdoors. What happened over the times looked like 4 simple stages. Stage 1, healing and voltage buildup. As soon as one side gets hot, the two ions start to separate. A net voltage grows with the temperature difference, even before you see the smoke. Stage 2, load on and current delivered. If we connect a small load or a comparator, the device delivers current while ions continue to drift. This is the moment we use for early warning. Stage 3, gradient removed, leftover imbalance. When the temperature difference goes away, the stored concentration difference can drive a small update voltage for a short time until the ions remix. Stage 4, cooling the returns to baseline. During cooling, the polarity returns to the original sign and the voltage decays to zero as the system relaxes. Okay, this slide is about fixing the interface so heat gets in fast and charges move with fewer collisions. Researchers always using layer by layer or immersion coating to build uniform interfaces even on rough substrates. The top layer is outer protective layer, which suppresses flame and serves as an oxygen barrier. At high temperature, it forms char, protecting the surface while keeping a clear temperature gradient for early sensing. The lower layer is conductive layer, which provides a continuous path for charge. When heat arrives, it builds voltage quickly, allowing a fast, self-powered alarm. With the mechanisms in place, let's see them in practice. This slide summarizes self-powered variable warning and self-healing coatings reported in some literature. Researchers print thin P and N-type thermoelectric strips on fabric. When the outside of the suit is hotter than the inside, the straps generate a thermal voltage, so no battery is needed. A tiny circuit reads that voltage and gives a vibration or beep. Placing the straps near hot spot areas such as shoulders, sleeves, and chest gives the earliest cue for firefighters and first responders. If the coating is cut or cracked, mobile groups in the polymer and a little moisture from the air migrate to the damaged zone. They form new hydrogen bonds, so the electrical path reconnects and the warning function returns without replacing the patch. The healing can repeat for several cycles, depend on the humidity and the temperature. This page shows how groups use self-powered thermoelectric nodes in forests. Small thermoelectric patches sit on poles, trees, or fence posts. When a hot front passes, the patches make a direct voltage and a tiny radio sends an alert. Because the nodes use very little power, they work off-grid for long periods. Some teams add a small solar panel only for the radio and the gateway. To survive weather, the coatings are made hydrophobic and encapsulated, so wind, humidity, and changing temperature do not break the signal. Data can travel by cellular or satellite to a phone or a dashboard. Here the idea is to place thermoelectric coatings of fabrics on eaves, vents, and rooms with higher risk such as kitchens and garages. The alert path is flexible. A local buzzer can sound. A phone app can notify the user, and the message can go to the cloud and onto the fair services through 4G or 5G. To avoid heated metal and hot pipes to cut false alarms, keep very short or use wireless links, and plan for simple cleaning and adhesion checks so coating stays reliable over time. Here are still some challenges. The first is outdoor durability and stability. Sunlight, moisture, thermal cycling, and abrasion can change the film and the adhesion on real surfaces. The second is selectivity versus false alarms. Sensors must ignore sun heat metal and hot pipes, but still react to early fair heat. That needs smart places, good interfaces, and clean thresholds. The third is low gradient signals. Early cues are only a few millivolts. Cold starts, long waves, and noise mean careful buffering the simple, reliable readout. The fourth is skill and standards. Large uniform coatings on wood and textiles are hard. Real deployment also needs certification and building code alignment. With these challenges in mind, the path forward is clear. Mechanism-guided materials combine energy filtering, ion thermoelectrics, and tuning doping with stability as the first requirement. Interfaces and encapsulation speed up heat coupling, use weatherproof char-forming topcoats for protection and repeatability. Hybrid sensing with HAI, fuse thermoelectric with gas or infrared sensors. Run anomaly detection at the edge to cut false alarms. Self-powered IoT pilots deploy on wetland, urban interface lines, and building use formats, track lead time, false alarms per site per month, and performance after aging. Solve this for items, and early self-powered fair warning becomes practical at scale. This review is published on Advanced Materials Journal. Okay, that's all I want to share today. Thank you. Thank you all. Anyone want to ask some questions?